It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
What was that? And I am Ray, as usual, and we welcome you back to episode number 97. So close to those triple digits, where today we're just going to be talking about some classical mechanics.
That's right,
Yeah.
classical. The classical world where everything is determined. There's something called Laplace's Demon, and it's something that a lot of people love to think about because once we got to the 18th century, people started thinking about gas particles and, they didn't really know that much about atoms. So they were just, trying to figure out properties of the very small things in this world. And so Laplace's Demon is basically an entity that knows the position and momentum of every single particle in the universe. And so it was thought at the time that Laplace's Demon, given his knowledge, he could predict the state of the universe at any point in the future and at any point in the past. However, due to recent modern discoveries, we found that, even if you do know the position and momentum of every particle, even though that's not possible, but let's say it is possible, you will not be able to predict where the universe is going, nor where it came from, due to chaos and nonlinear effects and turbulence and things like that. There's a great Veritasium video on that called the butterfly effect, which is, he talks about all this stuff. It's very, very good.
Classical mechanics is very interesting, especially when we talk about it, because we're so, or at least you are so always quantum, and we always end up in some episode talking about quantum mechanics. And
Quantum mechanics is cool.
No, I'm not saying it isn't. It's amazing, but
Brief intro on quantum mechanics. Here's the thing. The world is quantum. There is no such thing as a classical world. The world is quantum based. It's just classical phenomena that emerge from the quantum world that we live in.
I think it can be seen the other way too, though, that we live in it, because I think they're both just ways of interpreting our world. I don't think we live in a classical world. I don't think we live in a quantum world either. I think those are just ways of explaining the world we're in.
So, here's what I would say to that.
Okay.
Everything that you are made of and everything that not even you, I'm saying the entire universe, is made up of quantum particles.
Yeah, but okay, you're looking at the small scale.
I'm looking at what the universe is.
I'm looking
at what the universe is. The universe is fundamentally quantum.
It's fundamentally particle.
Classical phenomena like chairs and planets they emerge from quantum mechanical effects, like taking the limit as the amount of particles go to very high numbers, or the mass goes to very high numbers.
I mean, again, okay, you're describing like the quantum world that we live in. I agree with you there, but like when I was thinking you're more like saying we live in, so we can describe quantum mechanics, but then if we're trying to make it a little more general, we approach the classical. I'm just saying like classical and quantum are just, if you think about it, like just interpretations of what our everyday life is.
If you want to be really approximative, then sure, use classical mechanics.
No,
it's
I mean,
good.
That's the whole point,
it's
right? I
good.
think that's where it started. Like the whole thing was originally, I guess, also you can't really determine every particle. So when we have like a glass, we don't know the exact number of things here and there, the amount of
that's why
electrons
we use
bombarding. So we approximate
mechanics
with classical mechanics.
That's why we use it.
Yeah.
But I'm saying that the world is quantum. We look at it classically, but it is not classical. It is quantum.
Is quantum. Strong statement, but I guess we can move on. I guess we can move on. Okay.
All right. Before getting into the rest of this podcast, we have a little bit of news. You might notice that today's episode is a little bit shorter. That's because we don't have that much time. Turns out that university is it's a very busy thing to have going on in your life. And we've got homework, we have lab reports, classes, and other things. including something in 40 minutes. And so this episode is going to be like 45 minutes or something like that. But yeah, anyways, before we get into this, we have a little bit of news. We recently hit 22,000 followers on Spotify.
Woohoo.
So thank you everybody for that.
Let's go.
Other than that, everything is going well. Comment of the week. We didn't get that many comments this week, but if you want to be next week's comment of the week, make sure to leave a comment down below. This week's comment comes from Jasmeet Walia.
Hey.
He says, very interesting episode, very informative. Keep them coming. Don't worry about that. We will keep them coming.
We will keep them coming. Anything else? Also, we did announce on Instagram our apologies for the late NFT drop. just so much work, sometimes we don't remember all the things we have to do on certain days, certain dates. So it's dropped, and now instead of this episode, obviously we're going to be talking about it and releasing the winner next episode. So the very first NFT winner already has their NFT.
Yep.
Right, exactly. Yep. So congratulations. That's amazing.
By the way, it's on Cardano. It's a Cardano blockchain NFT. So if you end up winning, it's not an Ethereum one.
Probably just let you know. Yeah, exactly. But much lower gas fees and all too, right?
Yeah.
Yeah. Okay. Beautiful. So, anything else?
I think that's everything. So let's get into it. I think first of all, when we talk about classical mechanics, we're talking about F equals ma.
That's as much classical as you can get.
Right. That's where it pretty much started, saying that the sum of forces on an object is just a mass times the acceleration. And yeah, it's a pretty simple statement. You learn that in high school. They give you a situation where, you have a block, someone's pushing on it, and then it's also falling due to gravity, and then you got to calculate like its trajectory or something. I guess that would be a little bit more complicated.
Yeah, no, the falling block would be a little more complicated. I think the simple example is, just take any cart, like a frictionless cart, and you put it with like 5 newtons. What's the initial acceleration, for example, is a much easier idea. And I think also what that it also states that the sum of all external forces is equal to ma, because that's also important, because a little bit later on you also come to internal forces in a system, and you come to the astonishing result that internal forces don't actually matter at all.
Yeah, but this is the reason why you can't jump and like push yourself and then like go in a direction.
Exactly.
Or if you're in an elevator, you can't. We've had this conversation.
We've had this very same conversation.
But anything that happens, you see those like stupid posts on Facebook where it's like, oh, like just stand in a bucket and then pull the sides up so you'll float. It's like, no.
Wait, stand. I've never seen it. Stand in a bucket and pull the sides up.
You stand in a bucket and like you hold the lever, and then you pull on it, and then you'll move up. It makes no sense.
What?
It's
that's just not how physics works.
The forces are all in the system, and so it's all internal, so it doesn't matter. And this is actually true in general. Like, if you consider the entire universe as a system, then like nothing interesting really happens, because everything just cancels out. Under the assumptions of classical mechanics and not an accelerating.
There are a lot of
universe.
Exactly.
What would that mean? What would that, if the universe accelerates? Like what would that mean?
Well, I mean, it is accelerating in our latest theories.
But like, is there a force, an internal force that
dark energy
is causing it to accelerate? So I guess F equals ma doesn't count in that case, because the internal force is making something accelerate.
No, but I guess I don't think dark energy is okay. Yeah, I don't really know.
No, but there's a whole bunch of like other things that don't really make sense, because in this case, we're not talking about an object accelerating. We're talking about the boundary of existence accelerating. So like, is that even an object?
It's not. Yeah, because there was the whole thing about like information traveling faster than the speed of light, but then that's not really information. Like the whole quantum thing, entanglement. So like, I think that kind of might be in the same line as this, that it's just the boundary. So it's not like a physical object that's accelerating. So that's why technically the boundary is, I think, like relative observers is like accelerating faster than the speed of light, right? So I'm pretty sure at at some point there's literally going to be the boundary to someone accelerating faster than light, which makes no sense, which is why it doesn't exactly get covered under the information. So it can do whatever it wants. It's kind of like outside the bounds of what we say are objects.
But yeah, I guess coming back to classical mechanics, you learn in high school about forces, friction, and energy. Energy is actually really interesting, and actually, I don't know if we're going to get to this today, but we're definitely going to make another episode about Lagrangian mechanics and also Hamiltonian mechanics, because those are so beautiful. And the analogy in like from electrodynamics is so awesome. How in electrodynamics or just electrostatics, you have the electric potential, which is just a scalar potential. It's just one value. It just has a scalar value at every point in space. And then when you get to magnetostatics, you have a vector potential, where the potential is described by a vector at every point in space, which is harder to calculate just because it's a vector. And also, you know, it's just like weirder in general. But now, same thing with, well, the point of saying that is that it's much easier to deal with scalars than vectors. And in the case of Newtonian mechanics, F equals ma, you're figuring out, like in solving a problem, you're figuring out the forces, which usually are three-dimensional vectors acting on an object. And so you're gathering up all these three-dimensional vectors and then solving for the motion of your object. But you know what's easier than vectors is scalars. And you know what's a scalar? Energy is a scalar. And so when we do end up talking about Lagrangian mechanics later on, we're going to see how instead of gathering up all these three-dimensional vectors, you can gather up instead properties of the system that are one-dimensional, just scalar values, like the kinetic energy and the potential energy. And then from there, I'm not going to get into all the details of it, but you can get the exact same equations from F equals ma, but through energy.
So I mean, I think we could like dabble on into it a little bit later on this episode, because I mean, Lagrangian mechanics is classical mechanics.
No, it is, yeah. It's just a different way to do it, right?
Yeah. So okay,
because it's equivalent. We actually showed
one way. Okay, if there's anything to be known about classical mechanics for, let's say, people that are listening that are like, what really is classical mechanics? It's really a culmination of multiple different techniques. The very first one, the Newtonian mechanics, is kind of like the forefront of classical mechanics. Yeah. I believe there probably was multiple scientists before that started it, but
nowadays though, Newtonian mechanics is pretty synonymous with classical mechanics, because you don't touch Lagrangian or Hamiltonian until you get to third year.
No, but remember, Lagrangian is very basic classical mechanics.
No,
too.
I know, but there's no way anyone's going to know about that before they get into...
Oh, yes, for sure. Before they get into any higher academic, for sure. But yeah, so Newtonian is what like everybody knows, everybody's familiar with, because it's also like the easiest, also because it comes from just the first three principles, which make a lot of sense. Like the very first law, like that's basically like, if you think about it, like the first principles of classical mechanics, like Newton's first three laws. And they kind of describe a lot about how the universe should work.
And you know what's funny is that if you were to plot the difficulty of problems that you can solve versus difficulty of the method versus difficulty of the problems that you can solve, the Newtonian method has a very high gradient. But it intercepts zero. Of course. It intercepts zero, meaning beginners can start. But
I understand.
The gradient is very high, meaning as soon as you start to get a little bit complicated, like it becomes so difficult.
Because the moment your system gets complicated, as you just said, you have to take into consideration all these three-dimensional forces.
Exactly. But at some point, it makes more sense to switch to Lagrangian mechanics, because the intercept is actually not zero. It's very high, which means like beginners can't start there, but the gradient is much lower, which means that when Newtonian mechanics, that line intercepts the one for Lagrangian mechanics, it makes so much more sense to just hop onto the other one, because now you can start solving much more complicated problems without putting in that much more effort, because you understand how it works. Now it's just applying your like you have a question where it's like a rope around a pulley doing a dance, and you just apply all the things, all the kinetic, the potential, and then you just plug it into the thing, and you're done.
And next step from there becomes Hamiltonian mechanics. That's even another step farther. That
I haven't even gotten there yet.
It mainly is, again, I mean, if we are familiar with the Hamiltonian from quantum mechanics, or, I mean, technically you shouldn't be doing quantum before this, but we did, so it's funny.
Why not, though? Like, why? It's two different ball games.
I guess you're right. I guess you're right. But it's just interesting to see that, well, the Hamiltonian from Hamiltonian mechanics and classical mechanics is representing the Hamiltonian of the system, which is what we see in quantum mechanics. So in quantum mechanics, we're told that the Hamiltonian is kind of like an evolutionary operator. It's telling you how much energy a system has. And that's basically what the similar thing in Hamiltonian mechanics is in classical mechanics. However, the advantage, and again, we're not going to get into this, neither do I really understand the exact implications and the real depth of it, but the biggest advantage of, well, Lagrangian mechanics versus, let's say, Hamiltonian mechanics is that, well, Hamiltonians, again, they commute. They work with quantum operators. They work with things that we're used to. So the Hamiltonian, I mean, a more scientific way of saying it is that the Hamiltonian can be quantized, but the Lagrangian cannot. Like, cannot always be quantized. So what is usually done is first converted to a Hamiltonian via a transformation, and then you do all this analysis. So it's pretty cool why we do it and like these different steps. But you also might be asking yourself now, well, okay, I get it that, it's a little hard. They're hard steps, but like, what are these steps for? Like, we're understanding that, okay, F equals ma. But like, what am I learning about the system from this particular equation, right? And that comes from equations of motion. Right, I mean, we can kind of dabble into that because I think that is the fundamental concept of understanding what's actually happening in a system.
Because they don't tell you that in high school.
Not at all.
What they tell you is, okay, so F equals ma. Once you have the acceleration, then you find like the initial velocity, the initial position, and then you can plot out its motion or whatever. But it turns out motion is a lot more complicated than that, and so we have these things called equations of motion, but they don't explicitly tell you like where the particle is and where it's going. It just tells you the rule that it must follow, no matter where it is, and no matter, or I guess it could depend on where it is, but if you, like I'm saying, no matter where it is, as in you can say it's here and it will follow the rule that the equation of motion gives you. So yeah, equations of motion, they come from F equals ma, at least in the beginning, when you learn about equations of motion. And the reason is because F equals ma, as spoken about in another episode, are differential equations. Second derivative of position with respect to time is acceleration. Okay? And so it's pretty straightforward. Well, the thing about differential equations is that there is no general solution to a differential equation. There are ways to solve specific differential equations. But if you were to give me a function of, let's say, time and position and velocity, acceleration, ... there's no general solution.
Like, there's no general way to solve, you mean? Or
okay.
No,
like general solution. I'm saying,
I guess, yeah, you're right. I think we did
like
mention this on the podcast.
If you just have like some random amalgamation of terms together, and you say that's equal to 0, like there's no way for you can solve it numerically, but that's not really an analytical solution that we love. But there are specific equations. For example, linear equations, which we love very much, because F equals ma for easy situations is usually a linear thing, or you can even approximate it as a linear situation. So, for example, I think the biggest example that you revisit time and again in university is simple harmonic motion. just a mass on a spring. The reason why it's so important is because you can learn about, how the equation of motion changes and how to deal with those changes. And also, not even just that. Let's say you have just a mass on a spring, and then we say, okay, what if we consider the air friction? Then it'll slow down. The oscillations will get smaller and smaller. Well, let's see how that term fits into our equation of motion. And then let's see the things that arise from that. Also, then we ask, what else can we put in there? Well, what if we have a driving force? So somebody is forcing the spring to go at a certain frequency. And then what comes out of there? Well, you get things like resonance. You get things like destructive interference, where, the spring could just, the mass could not move at all, even though there's, something counterbalancing or counteracting it. It just still won't move. And then we're definitely going to talk about coupled oscillators in a little bit.
No, but we can also further continue on to because these damped oscillations can also have certain properties, right? It can be underdamped.
Oh yeah.
Can be critically damped. It can be overdamped.
Yeah.
And these are all, I remember this from differential equations. Do you remember exactly what they have? Because they're different properties with different.
Yeah, we actually did this in last semester. I can find it.
What?
No, I mean I did.
Oh, you did. Okay.
I did this. But yeah, so underdamped is a property that basically it's like long-term dampening. Essentially, you'll see a lot of oscillations before it goes to zero. And that may be something like a mass, just like a block on a spring. You see that if you pull it down and let it go, it won't immediately go straight to equilibrium. It'll do some oscillations. And then something like overdamped is maybe like the same situation, but in maple syrup. So that if you let go of the mass, it'll kind of just slowly return back to equilibrium, and it won't oscillate at all. And then you have something called critically damped, and this is just kind of the fine line between overdamped and underdamped. And it's pretty mathematical. I don't recall if there's a way to tell what the difference is, but I think it's possible to see one oscillation.
Yeah, that's what I'm saying. I think there's a difference. When you actually see what's happening, you can tell which one it is. I just forget on the top of my head which one is, because I remember
No, but I'm just talking about critically damped.
Yeah, no, but I'm talking for really all of them. For one of them it oscillates, right? For one of them it oscillates once and then it goes to zero.
Yeah,
right?
That's critically damped.
That's critically damped, right? It goes apart from it goes cross axis and then it goes to zero. And this is, again, I'm just talking about how the solution looks. And then finally we have, is that over?
This is in phase space. So here's multiple velocity and position, and so there are multiple oscillations. The critically damped one is the black one, so it kind of gets a little bit of velocity.
Right. Okay.
Anyways, there's a lot of different setups, a lot of different initial conditions. It is possible if you have an initial condition where the velocity is really high and it's critically damped, then it will go past equilibrium and then return back the other way. But that won't happen for overdamped.
Yeah, I think it definitely matters. And all of this comes from a simple characteristic of differential equations, really. So these equations are these spring equations. I don't know if we do spring. Yeah, we did F equals kx, right?
Did we talk about that? Is that what you're talking about?
No, I'm just talking about spring equations and how you get from there to understanding these underdamped and damped conditions.
Yeah,
because understanding that is basically just understanding the property of negative square roots. Because all of these critical and overdamped is just when the dampening factor of the dampening factor, is it of the spring or is it of the mass? I think it's the dampening factor when it's equal to something, when it's greater than something. Yeah, coefficient is the correct word. When it's greater than something and when it's less than something. So when it's equal to something, the square root is 0, and there's some properties of the general solution. When it's greater than something, the square root is positive, and now you have some new properties of the general solution. And when it's negative, you now have complex roots or a complex square root. So now you have even more weird properties about this differential equation. So it all stems from the fundamental principle of how it is defined, the force, or how the equation of motion of a spring is defined. And it's just got to do with second derivatives and first. It's just a differential equation, really. And what you're, again, solving for in this situation is you're just solving for, well, what is the equation of motion? And again, coming back to how important that is, all that's really telling you is how a specific object or a specific thing that you're measuring is evolving with time. If you take its derivative with respect to time and its second derivative, I believe you need like two derivatives, or, well, technically one time evolution is your equation of motion. And that's how you understand, or at least a little better, about how this one object can move throughout time.
We can also go do a simple example, because this is pretty easy to understand, right? Or I guess easy to follow along. If you, for example, F equals ma, we have a spring. F is minus kx, right? K is the spring factor, spring coefficient. X is the position. So minus kx equals ma, and we're just going to call acceleration x double dot. That's just how you say it. Now, if you put it on the same side of the equation, then you have mx double dot plus kx equals 0.
Mm-hmm.
Now, x is the position of the mass as time goes on. And as physicists do, we can guess a solution to this. So what is a function that when you take two derivatives of it, you get the same thing back, except minus sign, because we want it to equal 0.
Mm-hmm.
Also, little detail, if we divide both sides by m, then we just get x double dot plus k over m x equals 0.
Mm-hmm.
So then we want to take two derivatives of something, and we want to get minus, and then we need a factor of k over m, but twice, right? Because if we take two derivatives in, so we want a factor of square root k over m inside that function, and then we want those to cancel. The natural selection for that is a sine function or a cosine function. And if you set your initial conditions to be position at time 0 equals 0, then you're going to get an exact sine function. So then there you go. The equation of motion is x double dot plus k over m x equals 0. That is the rule that your spring system has to obey at any time. Now, using that equation of motion, you can find a solution for the position, and the solution for the position depends on your initial conditions. Now, this gets a little bit more technical because we're dealing with a second order derivative, or second order differential equation, which means we need two initial conditions, in this case, position and velocity. And depending on your position and velocity, we will get the exact function that satisfies the equation of motion and will tell you the position as a function of time.
Yeah, I mean, that's basically the whole process.
And this was the case for a spring, but F equals ma, this could be for any situation, right? If the force is tension with friction involved and air resistance and gravity, you just put all of those on one side, and then you say that is equal to m times the second derivative of x. And then most of the time, I guess all of the time, the forces are either functions of time. You can have an oscillating electric field that oscillates with time and doesn't depend on position or anything else. You can have a force which depends on the velocity, like air resistance. The faster you go, the more resistance there is to your motion. You can also have a force that depends on position, like gravity. How far away are you from the Earth will tell you how much gravity is pulling on you. And those are the three: time, position, and velocity. Mm-hmm. You can't have a force that depends on acceleration. I don't think that works.
No.
That doesn't make sense,
that
no.
Doesn't make, that doesn't make any sense.
There you go. So yeah, you just put all those things in. Now, notice how time, the position is a function of time. So that's an independent variable. We have position, which is something we're trying to solve for. We have velocity, which is the first derivative of position. And we have acceleration, which is second derivative of position. So everything is related to the position in time. So once you have your equation of motion, boom, you solve for the position as a function of time. But as we said earlier, this is not always possible. Sometimes you will have a differential equation where even if you plug it into Wolfram alpha, it will say no solution available because they just don't know how to solve it. But it might say, I don't know if Wolfram does this, but you might have a program that says, no solution available, but we can solve it numerically depending on your initial conditions. Because, you can plug in all your conditions into the differential equation and then see how the position evolves if you just increase the time by 0.1 seconds and see what happens to the position. And then you keep updating your position, you keep updating your velocity and all that stuff. And then you can kind of approximate how your object would move given this equation of motion.
So in this, in all of what we've been talking about so far, we've been discussing kind of the idea of position, velocity, and basically position and velocity, right?
Yeah.
Interestingly enough, in the real world, also, when people describe equations of motion and when people describe systems and how systems evolve, they also use similar variables. So any system, again, originally we were talking about the main point of doing a lot of this is to solve for that equation of motion, which is mainly two things. The equation of motion is actually something dot. When I say dot, I mean with respect to time. So derivative of something with respect to time. That's equation of motion. So when I say like equation of motion of like some particle's position, then the like x dot, like I'm finding how its position changes with respect to time. And in everything that we know so far, if we are given the positions of every particle in the universe, like you said, we would not be able to determine what happens next, because a key thing of what you also need with its position is its velocity, or how it changes with time. And another way of saying velocity is momentum. I mean, it's not really, but you know what I mean. Like,
kind of equivalent.
What I mean is what I'm basically kind of getting into is the definition of canonical variables. So canonical variables are like the variables in your system that basically your system depends on. It's two variables that will dictate the whole outcome of your system.
Did you do canonical transformations? Is that what you're going to talk about?
I mean, I'm not going to talk about them, but like, yeah, we did in the thing that
that's really related to canonical variables, yeah.
I'm just bringing up the idea of what a system is really made of, right? Because that's just what it is. Like when in the real world, like we're just talking about, okay, what we do in terms of math. But I think the biggest thing when people talk to me about math and when people talk to me about physics, a lot of times you're just thinking, okay, but how can this actually be applied? Like, what are we actually looking for? And classical mechanics is the one thing that you can actually do. Like, quantum mechanics so many times, like you're just really thinking, like it's like 16 dimensions, and you're just like, Wait,
when?
No, I'm saying in a lot of quantum experiments, like it's a lot of, okay, I guess there is experimentation as well, but you know what I mean? Like classical mechanics is not opinion, but is the one physics where you can directly see its implication. I push this glass, it's accelerating with a force. I directly see that implication. Can I test a particle in a potential well?
You could send a photon through an analyzer.
Can I?
Yeah, I mean, you can. You can buy polarizers on Amazon.
Okay, but that's not the same. I mean,
you know what you could actually do? You can buy 3 polarizers on Amazon. You can put one vertically polarized. You can put one horizontally polarized.
And diagonal.
And then you put another one in the middle. And then the question you ask yourself is, okay, I have a setup with 2 polarizers and 0 photons can get through both of them.
This is actually one of the physics experiments.
It is. So you have two polarizers. 0 photons can go through. So why is it that when you add a polarizer in between, you increase the intensity? Think about that. That is a quantum mechanical experiment that you can do at home.
Okay, why? Okay, wow. You make a point. You can do a quantum mechanics experiment at home. Point being, the classical is just a lot more interpretable. It's just a lot more interpretable. I'm saying, sure, there are experiments that you can do at home with quantum mechanics, but it's a little more difficult. In this particular situation, you let out a very easy one. But I'm just saying classical in general, like the whole point of it is that you can use it with macroscopic objects and macroscopic, phenomenon. Like you don't need to really look at the quantum effect. So all this again, basically to say that given a position and given a momentum, you can basically solve for whatever you want in your system. And in this situation, if you have, let's say, multiple particles or let's say you have multiple particles in a system, all you really have to do is know each and every one of their position and momentum. Now you might have realized something there. This violates something that we think should not be true. How can you know the position of each particle and the momentum of each particle? Because isn't that like the whole point of quantum mechanics saying, no, that doesn't work, right? So that's the interesting, kind of part from classical, and that's where it breaks off with quantum mechanics. Because in classical mechanics, we can and we do know the position and momentum of every particle in the system. But it's in the quantum world where these things don't exactly work out.
Are you sure?
What do you mean?
We know the position and momentum of every single particle.
Well, again, when you're talking about like that uncertainty statement, that level is so microscopic that it doesn't really do anything with classical objects.
But if you have like any rigid body,
yeah,
you're considering the momentum and the position of every single particle in that body.
No, that's what I'm saying. You can't do the particle thing. That's what I'm saying. You can't do it the particle way. But if you're talking about like different like many parts of your system, like if you're talking about this rod plus this rod plus this rod plus that rod, for example, and like their values is what I'm saying.
It's you were saying particle.
Well, I'm saying the ideal is that you do it with every particle, because that's what the formula is like. Okay, you have every part, you have all the positions, you have all the momentums. Boom, you got everything you want. But that's what I'm trying to say. The unfortunate part is that in the real world, we can't do that when it comes to particles. When it comes to that level, we can't apply the same theory to quantum mechanics. That's literally why, like, the physics is just different. Like that's why when people say like the quantum mechanics is different, not because it's literally because the physics written for the subject is a little bit different. Like it just doesn't work at the same level. There are different things that you need to know. And yeah, I mean, that's just a basic thing on canonical variables that I wanted to bring up. Yeah, okay. That's just a basic thing I wanted to bring up because I think it's very important for just a general idea of understanding what a system is made of, and just mainly understanding a system.
Non-linearity. That's a good topic. Okay. So back to oscillators for 1 second. Let's think about a pendulum. So if you really wanted to, you've probably done this before, but the equation of motion that you get is, we'll talk about angles. So we'll say theta double dot plus G over L sine theta equals 0, right?
Okay.
Now, this might remind you of the equation that I was talking about earlier with a spring. And this is because these are, both talking about oscillation. And so the equations of motions are going to look very similar.
Mm-hmm.
In this case, though, instead of having an x, right, something linear in x, you get sine theta, which is not a linear function by any means. So like what happens? How can we solve this equation? Well, the answer to that is yes. But there is something that you will get to know very, very well, and that is small angle approximation and Taylor expansions. So sine theta, if you're familiar with the Taylor expansion, starts with, right, sine theta equals theta. That is the first order approximation. And if we make that, that assumption that we have small angles, so the higher order terms are pretty much equal to 0, we can just look at the first term in the Taylor expansion. Then we have the exact same situation as our spring, because we have, a second order linear homogeneous differential equation, the solution to which we already know, especially because the coefficient of the theta term is positive. So we know it's going to be just a sine function, just regular oscillation, which is something we could have already set, right? But the problem is that this only restricts us to small oscillations, which is kind of boring, because in the real world, when you're swinging something around, you're usually just swinging it as however you want, right? Or if you're looking at like Galileo, you're watching a chandelier swing across and oscillate. It's probably not doing like small angles. So what happens when small angles are no longer applicable? Well, this is when we have to start looking at the higher order terms in the Taylor expansion.
Exactly. This is actually, interestingly enough, a experiment that I had to do for one of my classes, where I had to literally set up a pendulum and test the large angles. So continue.
Yeah. So what happens is that when we solve the second order regular small angle approximation differential equation, we get a sine term and we get a frequency of oscillation, right? We get one frequency, and that's what we see, right? The pendulum just goes across. However, if we start considering the next higher order term, and here's the thing, we can say that, okay, the amplitude of our oscillation is big enough such that the theta cubed over 6 term is relevant, but everything after that is not relevant. Okay, the theta to the power of 5 is still small enough.
Again, this is in the Taylor expansion, by the way.
The Taylor expansion.
Okay, yes.
Yeah.
And so, now, exactly. Now the big thing is now you can no longer say sine theta is approximately theta, which was the whole basis of understanding its equations of motion with small angle in the first place, right? And saying period equals L over G and all that good stuff. All those easy equations come from the fundamental fact that sine theta equals theta. But if that's not true...
Here's the thing. Now your equation is a lot more complicated. And another thing that we love to do in physics is to take things and just make them a little bit simpler, even though they're a little more wrong. But you just get to see the general behavior. And this is something that we do in astrophysics all the time.
Cal assumption right here. This is the one.
Astrophysics is hilarious. We just had a problem set where in the question, they just say, be very careless with your approximations. It literally said that. And so we were approximating, 5 equals 1.
Yeah, I was just going to say that. 5 equals 1. Like, that's the level of approximation.
Okay. What I'm about to say is not that crazy, but here's what we do, okay? We take our solution for the first order case, and we plug it into the cubed term to see what kind of things would happen, right? And the idea is that if you take your solution and you plug it into the linear term, then you just get your solution back. If you take your solution, you plug it into the cubed term, you're going to get those an approximation for those slight deviations due to the new term that you just added. And if you do the math, what you'll find is that an extra term comes out and you actually get a second frequency. And if I remember, it's 3 times the natural frequency of your pendulum. So now you have your solution involves the one term from that includes the natural frequency of your pendulum, and then plus another term that has a sine of 3 omega t, right? So it goes 3 times faster, but the amplitude is less. And so you can search up a bunch of diagrams about, nonlinear oscillations and things like that. And what you see is that now it's kind of, I think it's called period doubling or something like that. But basically, you'll get on one period, it'll have one amplitude. And on the next way around, it'll have a smaller amplitude. And then it'll go back up and then back down and then back up and then back down.
Wait, I'm actually remembering that's actually what I saw for one of my for one of my large angles, but I didn't actually talk about that.
Yeah. And if you now the more you increase the amplitude of your oscillation in general, now the theta to the power of 5 term becomes relevant, and you'll get 3 different amplitudes. And so now you're going to get, on your first run, it's going to be at some amplitude. And then on the second one, it's going to be a little bit lower. It might be lower or higher. I don't know. Depends on your initial conditions or whatever. Then you'll get like a smaller and a higher one. And as you can see, when you increase your amplitude to, I guess to very high numbers, what happens is that the amount of different amplitude peaks that you get just increases until your period for the entire oscillation, including all of the different amplitudes, becomes infinite, and it doesn't reproduce, and that's just chaos, right? If your oscillation never looks the same ever again, then you have something that is not predictable.
I don't believe you can have true chaos though in this scenario.
No, chaos, this is just an example to understand.
Okay.
You can have true chaos.
No, because chaos requires 3 degrees of freedom.
Yeah.
So in this case, in any kind of pendulum, I'm assuming you're assuming that you're doing it on a plane. It's planar motion. Exactly. Yeah. So then technically, like it's
still
an
1
idea,
degree
it's
of
an
freedom.
Idea, it's an idea for chaos, but it's not chaos.
Wait, I don't think
it's not chaotic.
I don't think it's degrees of freedom.
No, I know this for a fact because I literally
it's
remember.
Degrees of freedom?
Yeah, because he said very, very, very clearly. Well, one guy asked in this pendulum example, if we just take it past pi over 2, would it theoretically be chaotic? And he's like, if it's in the planar motion, if it's in your XY plane, fundamentally it cannot be chaotic, because just the way that we define chaos is with 3 degrees of freedom. And this is the way he said it, so don't take my word for it, but I'm assuming he's a professor, so he's probably right.
But I know what you're referring to. The way that I learned it is that you have your equation of motion. What you do is you decompose it into saying, like, let's say, okay, you have x1 equals x2 dot. And then you have x2 equals x3 dot. And then you just keep going down the line until you've listed out.
And that's chaos is what you're saying?
No. What's chaos is that you need at least 3 of these equations, and one of them has to be nonlinear. And so, for example...
So maybe it does require... I don't really know this very specifics, but I just remember him very clearly saying it needs to be an elliptic motion, like non-planar motion to introduce chaos.
Because, for example, like this might be contradicting what you're saying, but I can say that x1 equals x2 dot. x2 equals x3 dot, and then x3. Oh no, this case would only have 2 equations. Okay, what I'm trying to get at is in your equation of motion, you have x double dot equals minus GL sine theta, sine x in this case. So that's your description for, let's say, x1 double dot.
Okay.
That has a nonlinear term in it. Then all we need to get the original x, we just need to call, okay, x2 is x1 dot, and then x3 is x2 dot. So it basically just goes down the line. And then what you do is you solve for x1.
Hmm.
So, I don't know.
I don't know if
I
this
don't-
still
I don't
would
remember very
characterize
much.
chaotic, but it would still be an introduction to explaining like what it kind of means to be chaotic, because that's like that's kind of what it means to be chaotic, but it's not a chaotic system at that point technically. At least my understanding of it. One thing I did want to mention though before we ended the podcast, because this is maybe the most fundamental principle in classical mechanics, something that I think slipped from our minds, and this is definitely going to be a clip because it's insane, which is the principle of
Put that in the clip.
which is the principle of least action. I think this is basically what governs.
Wait, okay, hold on. I don't think.
What do you mean?
I don't think we can talk about that without talking about Lagrangian.
I mean, we've dabbled, like we've had a sentence into Lagrangian. I'm gonna make it. I'm gonna make it. I know we're very limited on time, but I just really think that in a classical mechanics episode, you can't not talk about this.
All right.
I just think it's crazy. So the most basic thing about Lagrangians that we've explained is basically it's just a difference in energy. And the Lagrangian is doing the same thing that Newtonian mechanics does. And it's basically, its goal is just to explain the way that a system evolves. That's basically it. Now, a Lagrangian, as Parker said, is no longer taking vectors instead of forces with Newtonian mechanics. It's taking scalars as kinetic and potential energy.
Wait, hold on. Can you just explain the Lagrangian and then do the principle of least action next time? Because I can explain the quantum mechanical reason why the principle of least action works, and I can't do that right now.
Oh, I just wanted. Oh, bro, like I think.
Because that would go perfectly.
Okay, just explain it too, because I think this is way too important to not include it. Okay, you're wasting my time. Thank you very much. No, okay. So, quickly but efficiently. So again, the Lagrangian is simply a difference in kinetic and potential energy, and it's doing the same thing that Newtonian mechanics is doing, or F equals ma is doing, but instead of dealing with vectors, it's simply dealing with a scalar. And what the Lagrangian is basically telling you is something that exactly we can get into in a Lagrangian mechanics episode. All I want to talk about here is what this action is, just really, really quickly, because I think, again, it's just very, very fundamental. The Lagrangian, again, is just saying from point A to point B, what is the change in kinetic and potential energy? That's like that's your Lagrangian. T minus V is your Lagrangian. T is your kinetic energy, V is your potential energy. The action is another mathematical quantity in classical mechanics that's simply basically the integral of the Lagrangian. It's basically taking all of the possible ways that you can go from point A to point B. Now, this can be, if you're just thinking in terms of, let's say, dropping a ball, you can think about it in terms of kinetic energy and potential energy. Like, you can do it in many different ways. You can throw it straight down. You can throw it up and then down. You can throw it horizontal then down. Okay, just think of different ways. You can have multiple different ways from reaching point B from point A. The principle of least action basically states that any object will follow the path of least action. That means to know what an object will do over time, that means how the object evolves from point A to point B, will be given by minimizing this function. Again, this function is basically just an integral, which basically is taking all the possible ways that you get from A to B. And the principle of least action is basically just saying that the actual way that this object moves is simply by minimizing this integral. That's it. That's the principle of least action. We will definitely discuss it more if we ever do happen to do a Lagrangian mechanics episode. I think we should do a more in-depth one with a professor. I think that would be really interesting. And we can definitely go much deeper into it. But I just wanted to say, or at least speak on this, because I think a classical mechanics episode without this principle is futile. So that's
I will
the
try to
principle.
get my professor.
That would be
for the
amazing.
next one.
That would be amazing.
Yeah.
Yeah, let's do that.
He's
That would
really
be amazing.
good at explaining
Is he?
things. Yeah.
That's good. That's good.
Yeah.
Okay, well, as Parker already mentioned, it's quite late. We have our class starting in 2 minutes, so we're good. But
So thank you everybody for listening to
Yes.
this episode. Make sure to follow us. Rate the episode 5 stars if you're listening on Spotify. Come subscribe, comment, all this stuff. We'll see you guys next time. I'm your host, Parker.
And I'm Ray. And we shall see you soon.
Bye, guys.